Now, for questions like this, right, okay, as I've always mentioned, any questions that involve energy, first thing we always have to take note of the conservation of energy. In this case, we have probably the electrical energy from the heater converting to the heat energy. Now, electrical energy in this case is still pretty simple, but most of the time, right, okay, for Cambridge, they can actually probably, instead of giving you the power rating of the kettle is 240 volts by 1500 watts, they can probably give you the current instead. So if they give you current, then you have to recognize that this electrical energy, now, electrical power is actually equals to VI. Okay, this is a more common problem because they will actually want you to recognize that electrical power can be P equals to VI. Okay, so in this case, then electrical energy will just be VIT. But of course, in this question, right, the electrical power is given as 1500 watts. So you can actually skip this step, and you know that electrical energy is just power times time, and that is equals to the heat energy, which is actually mc delta theta. Okay, and power is known, time in minutes, so you have to convert this to seconds. Mass is in kg, 1 kg of water. C, the specific capacity of water is 4200 joules per kg Kelvin. And the change of temperature from 20 degrees Celsius to 100 degrees Celsius. Well, so one thing that you notice is that PT, MC, delta theta, these are all given. Okay, that's why if you read the question, right, the last part of the question actually asks for efficiency. Okay, you will realize that this value that you compute is not going to be equal to this value here. So that's why there is an efficiency involved. The useful energy in this case is to heat up the water, and the energy that you supply is actually the power times time. So let's see. So here, electrical energy is power times time, so that's 1500 watts multiplied by 5 minutes multiplied by 60 seconds, and that should give me 450,000. 1, 2, 3. So I should have 4 zeros, correct? Joules. Okay, so that's the electrical energy that I supply. Then what is the heat energy that I actually have? Heat energy will be computed by mc delta theta. That will be 1 kg multiplied by 4200 what's that? Joules per kg Kelvin multiplied by change in temperature, that's 80 degrees Celsius, 100 minus 20, and that should give me 336,000 joules. Now, at this point of time, right, it will be actually useful to actually check, because the amount of energy that I supply cannot be smaller than the energy that I obtain. So if you make a computational error, then you will know that if these two values are, if the heat energy is larger than the electrical energy, I know something is wrong. Or in the event where I find that the heat energy is very much smaller. Okay, because a typical efficiency question, right, I will expect the efficiency to be about 60-70% efficiency. Although real world efficiency is about 55%. Okay, but it cannot go much lower than that unless you're talking about solar energy. Solar energy is about 30% efficiency maximum. Okay, but it still cannot be too small. So efficiency in this case, you can just calculate. Do I space here? Let me just draw a space here. Hopefully I have enough space here to do that. So efficiency, percentage efficiency will just be 336,000 over 450,000. Correct? That will give me, oh sorry, multiply by 100%. Multiply by 100%. So that will give me 74.7. Oh, that looks like a very nice value. 74.7%. Looks like a very nice value.